Okay, so if you remember, one of Jimmy's friends was getting kind of thirsty. So we said, all right, we want to be able to calculate, we want to be able to figure out how do we deal with a situation where we have two reactants. How do I deal with a situation where I have 100 grams of ethanol and 100 grams of oxygen? Fundamentally, what we need to figure out is which of those two reactants will I run out of first? Which of my reactants is the limiting reactant, the one that will stop the reaction because we ran out of it? Okay? It's the same process, the same stoichiometry type of stuff. If we think about this, if we imagine we had 5 ethanols. Let's go back to the individual molecules. Sometimes it's a little easier to picture what's going on. If I was going to react, say, 5 ethanols and 12 oxygens, okay? The ethanol and the oxygens react together in a 1-to-3 ratio to produce 2 carbon dioxides and 3 waters every time I burn up one of the ethanols. But in this case, when I started with 5 ethanols and 12 waters, I have an ethanol left over. This ethanol does not react. It is not used up. We call it the reactant in excess. The oxygen was the limiting reactant. It was the one we ran out of first. Even though we had different numbers, because it was a 1-to-3 ratio, if I had 5 ethanols, I would have needed 15 waters to completely use them up. So I need to go through, and I need to be able to do this not just with individual molecules. I need to be able to do this with masses, with gram values, because that's what we measure in the lab. Same process, same types of stoichiometry calculations, but we have to do a little bit more sort of chemical thinking about what do we calculate and what do our results mean. So if we go back to the idea of having 100 grams of ethanol reacting with 100 grams of oxygen, our new first step is to figure out which one of these two is the limiting reactant. Which one of the two is the limiting reactant? So we're going to say, all right, I pick one of the two reactants to start with. Let's say we're going to start with the grams of ethanol. So I'm going to set it up, start with one of the reactants. I'm going to start with 100 grams of ethanol, and I'm going to do a stoichiometry problem. And I'm going to do a stoichiometry problem that's going to tell me how much oxygen do I need. So I'm going to convert the grams of ethanol into moles. Then I'm going to set up the ratio to convert the moles of ethanol into moles of oxygen. And then I'm going to convert the moles of oxygen into grams. What this problem tells me, what this calculation does, is it allows me to predict, to burn up 100 grams of ethanol, how many grams of oxygen do I need? I need 208.4 grams of oxygen. So now I have to think. Once I know this value, I need to take this value and I need to compare the amount I need, 208.4 grams of oxygen needed. I need to compare that to the amount I have. I have 100 grams of oxygen. Do I have enough oxygen to use up all of the ethanol? No, I don't have enough oxygen. What does that mean? What will I run out of first? I'll run out of oxygen first. So all my calculations on the amount of stuff produced need to be based on what I run out of first. I need to base my calculations on my limiting reactant. I will have ethanol left over at the end. There will be unburned ethanol sitting there because there's no more oxygen for it to react with. So when I go through and calculate how much water can be produced, I need to start with the limiting reactant. In this case, I need to start with the oxygen. So, step 1 is, well, step 0, get a balanced chemical equation. Step 1, figure out what your limiting reactant is. Step 2, use the limiting reactant to calculate how much product will be used. So I need to start my calculation with the 100 grams of oxygen because that's my limiting reactant. Now I can go through and do the same process that we've been doing, convert the grams into moles, use the mole ratio, 3 moles of oxygen to 3 moles of water, then convert the moles of water into grams of water. From 100 grams of ethanol and 100 grams of water reacting together, you can produce 56.3 grams of water. Okay? Questions?
I'm just checking with the 6 thing.
Uh-huh. Yeah, this would actually be 56.31. Yeah, 4 sig figs. There's another new question I can ask you. How much is left over? How much ethanol is left over? You know how much you're going to use up all the oxygen. Oxygen is the limiting reactant. So the new calculation is how much stuff is left over. If I start with 100 grams of ethanol and 100 grams of water, I've already figured out that I'm going to use up all the oxygen. How much ethanol will I use up? What do I start with? I need to start with the limiting reactant. I'm going to start with the oxygen, and I'm going to calculate how much ethanol do I need to use up all of the oxygen. Same stoichiometry calculations. Convert from grams to moles. Use the mole ratio, 3 moles of oxygen to 1 mole of ethanol, 3 to 1. Convert the moles of ethanol into grams. I get a value of 47.99. This is how much ethanol I need to use up to react with all of the oxygen. How do I figure out how much is left? Yeah. I started with 100 grams. I used up 47.99. I have 52.01 grams left over. I can answer the question of how much is left. Okay? So, have a balanced chemical equation. They give you multiple reactants. Determine which one is the limiting reactant. Use the limiting reactant to calculate whatever they ask you to find. How much is left over, how much of this product will be produced. The key is the limiting reactant is where you have to start because that was what really limits or stops the reaction from happening when we run out of it. What if I wanted to produce water using galactose? If I had 100 grams of galactose and 100 grams of water, how much water could be produced? And what mass of which reactant would be left over? So how much water can I produce and what mass of which reactant will be left over? Same reaction, galactose with oxygen to produce carbon dioxide and water, starting with 100 grams of each one. All right, so let's take a look at this process, okay? Wyatt, find a seat, please. All right, we pick one of the 2 reactants to start with. I would recommend that you typically start with the reactant that has the higher coefficient. There's a slightly greater chance that that's actually going to be the limiting reactant. So that's the one I typically start with, but it doesn't matter you can get to the right answer either way. The question is, how many calculations are you going to have to do? So I started with 100 grams of oxygen. I convert the grams of oxygen into moles using the molar mass. Again, I have to do that because my ability to convert from one type of molecule to another depends on knowing how many molecules there are. I got to have the number of them. Moles is a number of molecules. These chemical ratios are based on numbers. I can't use grams. I got to get to numbers of particles. So, grams of oxygen into moles. Then I can convert from moles of oxygen into moles of sugar. I want to find out how much sugar do I need to use up all of the oxygen. Based on that answer, I can tell what is my limiting reactant. What will I run out of first? So I converted moles, 6 moles of oxygen, 6 from the coefficient here, 1 for the sugar. Then I can convert the moles of sugar into grams of sugar. Again, molar mass from the periodic table, 6 carbons, 12 hydrogens, 6 oxygens. So I find out that I need 93.83 grams of sugar. If you do this the other way around, if you start with the sugar, you find out you need 106 grams of oxygen. In either case, this shows me that I have more than enough sugar, or if you did the other calculation, you don't have enough oxygen. Oxygen is my limiting reactant. Okay, oxygen is my limiting reactant. I have excess sugar. I'll use up all the oxygen and have sugar left over. Then I can go ahead and remember this was how much sugar we needed, 93.83, how much we had. We had more than enough sugar. Oxygen's my limiting reactant. I'm going to start with the limiting reactant, and I'm going to go through and I'm going to calculate how much water. Same process. All of these are the same process. Take the grams, convert grams into moles so I can use the mole ratio from the balanced chemical equation. In this case, it's a 1-to-1 ratio. And I get 1 mole of water to 18.02 grams of water. So again, I get 56.3 grams of water. If I start with 100 grams of oxygen, and oxygen's the limiting reactant, it turned out that in both of these combustion reactions, it was a 1-to-1 ratio. So I get the same amount of water whether I burn 100 grams of ethanol with 100 grams of water, or 100 grams of sugar, sucrose, or galactose I should say, with 100 grams of oxygen. Because in both cases, the oxygen turned out to be the limiting reactant, and it was a 1-to-1 ratio, oxygen to water. Okay? Final step, I got lucky because I picked the limiting reactant to start this calculation. I didn't have to redo it. If you had started with galactose, which is totally fine, you get an answer that shows you that oxygen's the limiting reactant, but then you have to come back and do this calculation to find out how much galactose, how much sugar was used up. You take how much you started with minus how much you used up, that gives you how much is left over. Okay? Questions?
Wait, if my answer is like a little bit different.
Yeah, plus or minus a digit out here at the end is fine. That's a rounding issue. And whether I made it or you made it, this doesn't really matter. Okay? So this is important. Being able to do this limiting reactant stuff is important for a lot of reasons. Not just because we can get glasses of water to drink when we're thirsty. Okay? You've got homework tonight, 97 through 105 odd. I'd like to do a demonstration.
Wait, can you go back real quick?
All right, so I'd like to do a little demonstration of why this limiting reactant stuff turns out to be super important, okay? It is critical to being able to do the types of problems that we need to do on the AP test and things like that, but it's also fundamentally important for all kinds of industrial processes, okay? So, typical kind of reaction that we might look at, Okay? We might look at, say, the combustion of hydrogen with oxygen. Okay? Hydrogen and oxygen will react to produce water vapor. Okay? Hydrogen gas reacts with oxygen gas to produce water vapor. We'll balance it in just a sec. Okay? So this is not a balanced equation. This is just what is reacting with what. Okay? So what we want to do is I want to actually show this to you and show you what happens when you do a ratio that's good, a stoichiometric ratio, versus a not stoichiometric ratio. But to do that, I need to ask these people over here to stand up and scoot to the back of the room. No, just stand up and move to the back of the room. Yeah, leave your stuff. Yeah, maybe you too. Okay, so what we have, we're going to do each one individually first. Okay? We've got the oxygen. This is a balloon full of just pure oxygen. Okay? And what we're going to do is we're going to see what happens when we light it on fire. So what happened? The balloon popped, okay? Remember, oxygen makes up 21% of our atmosphere, okay? So there's already plenty of oxygen in the atmosphere as it is, about 21%, okay? So let's see what happens. Let's move to a balloon that is pure hydrogen. So this balloon is pure hydrogen inside, okay? So, what happened to the hydrogen? It reacted with the oxygen in the air. It reacted with the oxygen in the air and produced water. This process is pretty highly exothermic. That means it's water vapor. Well, yeah, we already had water in the room, but yeah. Okay, so it produces a lot of energy. What that energy did was it meant that the water that's produced is a vapor and it's at a pretty high temperature, which means that it's an expanding gas, and that's what gives us that pressure wave. Okay? Question. These are just normal balloons. I mean, what do you put in them is the key. So, is helium reactive? Does helium react with oxygen in the air? You should know. You should know. I taught you this already. How reactive is helium? It's not reactive at all. There are no known compounds with helium in them. It doesn't do anything. It would be just like the oxygen. It just pops a balloon. So, this equation shows us a 1-to-1 ratio. Okay, we know it's not balanced, but this is, let's say we did a 1-to-1 ratio of hydrogen and oxygen mixed into the same balloon? I put them there with a tank. We have tanks of hydrogen and oxygen back in the storeroom. If you can go to any welding supply store and buy this stuff yourself. It's not like
They sell it to minors.
I don't know, but I think so. So 50-50 mixture. 50% hydrogen and 50% oxygen. So, much more. I mean, that balloon had less hydrogen in it. It actually had less hydrogen in it, right? But it was a significantly larger explosion. Why was that? The oxygen was pre-mixed. The oxygen and the hydrogen were very close together. So what happened is the reaction took place much faster, and that generated a higher pressure wave. Okay? When we had just the pure hydrogen balloon, the oxygen had to diffuse into the mixture. It had to mix into the mixture from the air. Here we pre-mixed it so they could react faster. Okay? Now, if we take a look at this reaction, it really should be 2 parts hydrogen to 1 part oxygen to give us 2 waters. So the optimal mixture, the mixture that will use up the exact right balance of the 2, is one that has twice as much hydrogen as the amount of oxygen in the balloon. I think we have some of those. So, this balloon has roughly a 2-to-1 mixture. 2 parts hydrogen to 1 part oxygen. What we call a stoichiometric mixture. Okay? In the other one, half the hydrogen didn't get to react. Half the hydrogen in the balloon didn't get to react because there really wasn't enough oxygen pre-mixed with it. So, should think about what that means. So, not only is this a fun and exciting way to create water, it's also a great way to dust. So, the stoichiometric mixture, clearly, noticeably larger reaction. Okay? So, if you want the most amount of water, you want a stoichiometric mixture. Okay? The biggest bang comes from a stoichiometric mixture. This type of stoichiometry stuff, these types of questions are fundamentally important for all types of chemical reactions. Yeah.